Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. So what I want to do today is continue talking about p-adic numbers, but introduce the very important number field, function field analogy, and in particular show how to use it to give a geometric interpretation of our solution for Diophantine problems. So this number field, function field analogy is very, very important in arithmetic geometry. And so that's the reason why I want to introduce it today. Okay, so what's our setup? So our setup begins with a ring R. So I guess if you're interested in number theory, you primarily work with the integer Z, but sometimes you also want to be a little bit more general and work with rings of integers inside some number field, so some finite extension of Q. But what we'll also do is we'll work in a different context as well. We'll also look at the case where R can be just a polynomial ring in one variable x over the complex numbers. And this, remember, is also the coordinate ring of the affine line. And more generally here, you can put in the coordinate ring of any algebraic curve. So that's R. Sometimes we like to solve problems in this context here. Sometimes we prefer to work with the field of fractions, F. So in this case, Z, of course, that's just the field of rational numbers. And in this case here, you just get the field of rational functions, Cx here. Okay, so there's very strong analogy between these two rings. And why is that? Well, in both these cases, these rings are what are called Dedekind domains. So what are they? So firstly, they're commutative rings. They're both domains. They're also both Noetherian, so they satisfy the ascending chain condition. They're integrally closed. And the other thing is they have some type of dimension 1 sort of condition, which means that every non-zero prime ideal is actually maximal. So what that buys for you is some sort of factorization of ideals into primes, ideals, and in fact a unique factorization of that. So they come under this concept called a Dedekind domain, which I won't go into too much. But the main point is that there are strong analogies between these two. And what I want to do today is to show you how to use the analogy between the two. Okay, so what was the problem that we were looking at? Okay, so what's the question of interest? Well, the question of interest is the following. We're going to consider a polynomial, P, in n variables, y1 up to yn, with coefficients in our ring R, either Z or Cx, and we just want to solve for the zeros of this polynomial. Okay, so we'll solve for the zeros of this polynomial, and so the alpha 1 up to alpha n, they'll be inside R. That's one case here, and that's called the integral case, because in this example here we want to look at integer solutions. But sometimes we also want to look at solutions where these alpha 1 up to alpha n are in the field of fractions F, and we'll call that the rational case, because when you're in this case here, you get the rational numbers. Okay, so we can try to solve this, and we saw various things about trying to solve this equation over the integers. And one of the things that we saw is that it's often good to look at this equation modulo some prime number. So what I want to do is I want to try to interpret this idea geometrically. And the way I'll do that is as follows. Okay, so I want to look at the geometry of mod M solution. So this M will correspond in the integer case with a prime, but more generally it'll be a maximal ideal of one of these two rings. And also global solution. So what does global solution mean? So a global solution just means a solution over in one of these two rings, okay, an integer solution. And part of the point of this video is to explain why we call it a global solution. Why do we use this geometric word global? Okay, so to bring the geometry in, I want to see what happens when you look at this idea of looking at solutions modulo primes in this ring here. Okay, so that's what we'll do. Okay, so we'll start with R equals our polynomial ring Cx, and you can also think of this as the coordinate ring on the affine line. And to keep things simple, I'm just going to assume that our polynomial that we're going to solve for here has just one variable, so n equals 1. So we look at P of y, and that's a polynomial in y with coefficients in C of x. So what is this ring here? Okay, Well, since you're allowed polynomials in x for the coefficients of y, that means that that is just the polynomial ring in x and y. And so you can think of this polynomial as a polynomial in x and y with complex coefficients. Okay? So now what can we do? So you've got a polynomial in two variables now. Okay? And often to study this, remember we want to look at the zeros of this. What we can do instead is look at the zeros of this as a polynomial in two variables instead. So we graph P of xy equals 0, and we graph this in the affine plane with coordinates x and y. Okay, so let's just pick a little example here. So P of xy is x squared minus y squared. The way we really want to think of this is a polynomial function in y with coefficients in x squared. So the constant term, so to speak, is x squared, and there's no coefficient, zero coefficient of y, and the coefficient of y squared is minus 1. Okay, but now we can graph this in the xy plane, and it's easy to graph when this is equal to 0. Okay, if x squared minus y squared is 0, then x squared equals y squared. So either you have y equals x or y equals minus x. So let's graph them in here. So that's the graph gamma that we're looking at. So what do we do now that we've graphed the set of solutions to this inside the affine plane with coordinates x and y? Okay, so let me show you. So what's the question we want to have a look at here? We want to understand what does it mean to have a solution modulo some maximal ideal in the case where this ring is the polynomial ring in one variable x over c. So what are the maximal ideals in this case? Well, in this case, they're all generated by linear polynomials. And so you can write it as just the ideal generated by some x minus alpha for some parameter alpha, a complex number. Okay, so we're going to go modulo this prime here. And let's see what happens when you go modulo this prime. So if you look at Cx modulo this M, what type of a ring do we have? In fact, it will be a field since this is a maximal ideal. And hopefully you can see fairly easily that modulo this, you can reduce any residue class to some constant. So this is just the set of constants essentially. And in fact, as a field, this is isomorphic to the complex numbers. So here, if you want to look at a solution modulo M, you're just looking at a complex solution. Okay, and what does modulo M mean? So that means that you're treating this as equal to 0. So if x minus alpha is equal to 0, then x is equal to alpha. And remember what we were trying to do? We were trying to solve this polynomial is equal to 0. And we're going to work modulo M, so x is equal to alpha. So we can replace x with alpha here. So we're solving 0 equals, in this case, x equals alpha, alpha squared minus y squared. And we want to look for solutions to this in y, so inside our field here. And so we're just looking for complex solutions. And this is, of course, just a complex polynomial now in y. And so it's quite easy to solve what this is, right? So the solutions to this are just y equals plus or minus alpha. Okay, so that's the solution when you go modulo M, if M is this maximal ideal there. Okay, so let's have a little look geometrically what's happening. Okay, so basically what we do is we're solving for this equation here, but we just set x equal to alpha. Okay, so that means that we look at the set of all solutions, which I've graphed here as these crossing lines, and now we just look at the solutions where x equals alpha. So if alpha is here on the x line, we just look at the solutions which are here and here. Okay, so it's just this part of this graph where the x value is equal to alpha, that is on this abscissa here. And that's the way you should try to interpret and understand what a mod M solution is. Okay, so you should imagine if you're working even over the integers and you're trying to solve for integer solutions, you should imagine this type of a picture here. You draw the graph and you kind of think that for each prime number, when you go modulo some prime, you're kind of picking, you fix that prime and you look at just that part of the graph over that particular prime like this. That's how you should geometrically visualize looking at solutions modulo some prime. Okay, so let's move on to the next question, and that's to see what's a global solution, that is a solution in R. And hopefully when I've shown you this, you'll understand why we use the word global here as well. Okay, so now we're solving for our variable y. So y here now has to be inside our ring. And our ring is just this polynomial ring. So it's going to be a polynomial in x. Y equals f of x. And what does it mean to be a 0? So that just means that p of x comma f of x is equal to 0 now. Okay, so that's what we get straight away. But this tells us a way to visualize geometrically what's going on. Okay, so suppose you have a solution y equals f of x. Well, what are the set of all x, y where that is equal to 0? That's just this graph here, okay, where x squared minus y squared equals 0, these two crossing lines. And what you're saying is the set of points y equals f of x, so the set of points x comma f of x, that's inside that graph. But the set of points where y equals f of x, that's just a graph of this function here. So you're asking for a solution f of x just means that the graph of this function y equals f of x, that has to sit wholly inside this big graph of where x squared minus y squared equals 0. Okay, so hopefully you can see, I've chosen the example where it's easy to see, graphs of functions, okay, and in fact polynomial functions, which lie inside here. Okay, so one graph is, so you need a function, so it has to pass the vertical line test. So one of them is this one here. That's the graph of the function y equals x. And then there's also this graph here, which is the graph of y equals minus x. And so you can see is that if you want to solve for y as a polynomial in x, of course there are only two solutions, okay? The polynomial is either x or minus x. And we can see this now completely geometrically, okay? Okay, so the graphs of these two functions are inside this big graph here, okay? So now I want to explain why this is in some sense a global solution, okay? So why do we use the word global, okay? So what is this graph, okay? So to look at the graph, you're talking about the graph of a function. So for every possible input, x equals alpha, okay, you get a point on the graph. Okay, that's the point where x equals alpha, y equals f of alpha. Okay, so that's a point on the graph, and since this graph is contained inside this big graph gamma, that means that you get a point on the big graph gamma as well. And since you fixed x equal to alpha, that just corresponds to a mod m solution, where m is this maximal idea x minus alpha. Okay? So that means for each and every point on this x line, okay, and this x line, remember, corresponds to the fact that this is the coordinate ring of the affine line with coordinate x. Okay, so for each and every point in here, what this solution does is it gives you this function value, in this case a polynomial function value, f of x, which sits on this big graph gamma. Okay, so what you basically want to do is you want to piece together mod m solutions for every possible m, okay, and the changing m means you just change this alpha. So for each alpha here, you pick a point on big graph gamma. So you can pick, well, if you're over here, you can pick this one or this one. And then as you slide it across, you pick a different one. Now, of course, each time you get a choice of two. Now, if sometimes you pick something on this one and sometimes you pick something on this one, you can't make a global solution. which is a polynomial function. You can make a function that way, but it won't be a polynomial function. Okay, so if you want to have a graph of a polynomial function, okay, basically what you have to have is you either have to have this function here, y equals x. Okay, so once you've chosen, for example, this solution modulo this x minus this alpha, then all the other solutions have to be the ones on this line. Or if you pick this one, you have to pick all the ones which are on this line. But that's the key point. Okay, so that's why you call it a global solution, because it means that on the whole of this affine line, and this ring, remember, is the coordinate ring of that affine line, for each of the points on this affine line, you pick a solution which sits above it. Okay, and the only extra thing that you have to do is to make sure that you pick them compatibly, so you get a graph of a polynomial function as opposed to just some random function. So when we're solving Diophantine equations, we saw that sometimes it's a good idea not just to look at solutions modulo some prime number, but also looking at solutions modulo powers of that prime. And if you look at all powers of that prime simultaneously, that's equivalent to solving in the ring of p-adic integers, which is the completion of the ring of integers at that prime number. So what I want to do is to show you a geometric interpretation of what you are doing when you're using that technique. So to look at that geometric interpretation, again, we work over the ring of polynomials in one variable x with complex coefficients. And when you do completions, in this case at a maximal ideal, you end up with power series. And the power series expansion will be about, or whatever point you're looking at, which corresponds to that maximal ideal. Okay, so let's look at a little example. I'll vary the polynomial that we use now. So the polynomial will be y squared minus x, and as usual, it's going to be important to graph the zeros of this in the whole xy plane. So let's do that. This is easy enough. So I guess this is a parabola, but now the usual coordinates are switched around, so it will point to the left. And there we have our parabola. And what's important here, I guess the best way to understand these power series solutions is actually to recall the implicit function theorem that you should have all seen in your several variable calculus course. Okay, so I'll state a simple version of this, maybe slightly different from the usual one. So suppose you have a polynomial in x and y with complex coefficients, and we're going to assume some conditions. So the first one is that we have a zero of this. Okay, so p of alpha beta is equal to 0. So that just means a point on this curve. Okay, so we'll pick a point here, alpha comma beta, which lies on the curve. And then what will we assume? We'll assume the following, that the derivative of this polynomial with respect to y at that point is non-zero. So what does that mean? So if you look at the tangent line here, you want to make sure that this isn't vertical. Okay, so that's the key point there. So because it's not vertical, of course, this graph here looks locally like this tangent line, so it's locally invertible. So around here, locally, you can invert it. So more precisely, the statement is the following. The statement is that you've got a kind of function which describes locally what's happening here. That's f of x. It's a holomorphic function. So there exists a holomorphic function. It's only defined on a neighborhood of this point x equals alpha. So there's some neighborhood here. And basically, if you look at the graph of that, it lies inside here. Okay, so it lies inside there. Okay, so to sum up, what are the key points? So firstly, this solution sort of extends the solution that we had, alpha beta. So the graph of this goes through this point, alpha beta. So f of alpha equals beta. And the graph of this function does lie inside here. So p of x comma f of x equals 0. So in this sense, this holomorphic function gives you a solution to this polynomial equation. And what's more, since it's a holomorphic function, you've got a power series expansion around alpha, so it's in terms of powers of x minus alpha. You can do a power series expansion like that. Okay, so let me reinterpret this, and this shows you what you're doing when you're looking at power series solutions. Okay, so what's going on here? So what is this y equals f of x? The way to look at it is as follows. The way to think of it is you think of this as a power series. You can write as a power series expanded around x equals alpha. So it's an element of the following completion of your ring Cx. It's the completion at the maximal ideal M, where M is the principal ideal generated by x minus alpha. And the point is it's related to this modulo M solution. So remember, if you have a point on this graph which sits over x equals alpha, that's a mod M solution where M equals x minus alpha. So you've extended it a little bit in the neighborhood of that. So that's what you've done, okay? So it's a power series solution that extends it in a neighborhood of that point alpha beta. Now there's some differences between the formal approach and the approach here. So here we're looking at calculus. When you talk about holomorphic functions, you usually have some sort of convergence. So there's a slight difference here. When we look for power series solutions inside here, of course, we don't care about convergence at all. Okay, but at least it means that when you use this, you do get a solution in this sense. Okay, so let's look a little bit more at this example here to see what's going on. And let's see what happens at alpha beta equals 0, 0. So if x and y are both 0, you do get a point. So you get a mod x solution, a modulo x solution. But note that the conditions don't hold. The tangent here is vertical. And it's just as well. Otherwise, you could get a power series solution. And I claim that actually the power series solution here doesn't exist. Why is that? Well, remember, you want to solve for y as a power series or whatever in x, some sort of function in x, depending on the situation here, a power series. And of course, the solution would be as a function y equals the square root of x, and you can't write that as a power series in x. Okay, so when you're thinking about why do power series solutions not hold sometimes when you have solutions mod M holding, well, this is the type of picture that you should be thinking of. Okay, so this is the geometric viewpoint that you should have when you're trying to solve Diophantine equations in the p-adic integers. Okay, you're trying to extend basically modulo p solutions, and you should visualize it in this sort of way, as sort of in a neighborhood of that point. And of course, if you want to try to get some sort of global solution, the basic idea is you want to try to patch up all these local solutions together. So this is a very, very important principle in number theory, and it doesn't make too much sense if you think purely in terms of numbers, but the interpretation when you go to the geometry is absolutely clear. Okay, so I want to talk about one final thing about this geometric viewpoint of solving Diophantine equations, and that's this idea of solutions at infinity, which is a rather funny sort of a thing. But again, in the geometric case, it's very, very easy to understand. Okay, so now remember we're trying to solve a polynomial equation like this, but suppose now you want to look at solutions not inside your ring, but inside the field of fractions. So let's look in the first case, the geometric case, where you look at the field of rational functions in X. Okay, so again, you can look locally at each point and even complete locally at each point. So any solution here will actually give you a Laurent series solution, and that Laurent series solution you can write out about any point inside your affine line. But not only that, you can also write it out as a Laurent series solution. I guess maybe it's better to write this as any alpha inside here. You can also write it as a Laurent series in X inverse, which means a Laurent series at alpha equals infinity inside the projective line. So that means that you have an extra condition here that you can play around with, an extra point that you can play around with. So when you study this geometric picture, actually it's important not to look just at this affine line here, but to look at the whole projective line. And that's one of the reasons why projective geometry is important, is that it can give you extra conditions and you'll understand the situation better. So the thing you should really do here is actually extend this graph so it has an extra point at infinity. And when you do that, you'll get the real complete picture of what's going on. Okay, so that's easy to see what's going on geometrically. And the point is, well, what about in number theory? Okay, so in number theory, suppose now you're not looking at solutions over the integers, but over the rational numbers. Again, each such solution will give you a solution over the p-adic rationals. But can you take p equal to infinity? Well, it turns out that there is an analogy for that as well. Given any rational solution, you also get a solution over the real numbers. And the correct way to kind of interpret that, as there's the analogy unfortunately doesn't become quite so close, is you should kind of think of the solutions over the real numbers as like solutions at infinity. Okay, so to sum up in this video, what I've done, I've looked at the geometric viewpoint for studying Diophantine equations, and I hope it gives you a good way to visualize the techniques that we are using to study Diophantine equations. And what this means is that it allows us to frame our approach in interesting ways and also suggest new ways of attacking the problem at hand. And in fact, in the next video, what we'll see is that here we've got some theorem which is clearly of a geometric or calculus nature, in fact, the implicit function theorem. And it's highly suggestive that maybe there's a version of this that will also work not only when you work in this ring of polynomials in a single variable x, but over the p-adics as well. And that's something called Hensel's lemma that I'll show in the next video. I hope you enjoyed this adventure in pure mathematics.